We go with the second lesson. I know it says period 3, but don't worry about that. So, the second lesson, we're going to talk about the different variables affecting gases. And those are pressure, volume, and temperature. So, the first variable we're going to talk about here is we're going to talk about pressure. Pressure is the force per unit area. We've talked about that before. This was a demonstration where I leaned against somebody with my palm versus a pencil. Pressure can be measured lots of different ways. Pressure is air pressure we're talking about. Pressure can be measured in kilopascals and or atmospheres. Table, in your reference table, table A has kilopascals is 101.3 kilopascals, and atmospheres is one atmosphere, 1 to ATM. Those are the standard units in chemistry, but there's a whole bunch of other ones you guys probably know about. PSI, pounds per square inch, like you're pumping up a bike tire. The weather people, they use millimeters of mercury or inches of mercury because they're literally measuring the column of a barometer, mercury barometer. A couple other ones here are bar and torr, 101.013 bar and 760 torr. Those are also pressure units. So you've probably heard of those before. Earth Science, I think, uses isobars. So they talk about isobars meaning air pressure. That's what they're talking about here, isobar. So that's pressure. The next unit is volume. And as you know, volume is the three-dimensional space that something occupies. We would use, in chemistry, we would use the terms measurements of liters or milliliters or possibly cubic centimeters, which is a cubic cm or a cc. Cubic centimeter is the same as a milliliter. Another one's possible is cubic decimeters, dm to the third. A cubic decimeter is equivalent to a liter. The medical industries, they use cubic centimeters and cubic decimeters when they're talking about volumes of gases and volumes of different things, because it's a more precise term than liter or milliliter. But regardless, liter, cubic decimeter, basically the same thing. Milliliter, cubic centimeter, basically the same thing. A liter is 1,000 times greater than a milliliter. The next unit is temperature. Temperature, as you know, is the measure of the average kinetic energy, and temperature can be measured in either degrees Celsius or in kelvins. Now, for the gas laws, we have to use kelvins. Now, the way we intertwine all three of these variables together is something called the combined gas law. Pressure times the volume over the temperature in the initial conditions are going to be equal to the pressure times the volume over the temperature in the Kelvin over the final conditions. And temperature must always be measured in the Kelvin scale. The reason for that is Celsius has a 0 in the middle. And as you mathematical geniuses know, putting a 0 in the bottom, the denominator, would wreak havoc on our formula. So Kelvin has no 0, that has no negative values. So it's an absolute temperature scale, or the thermodynamic temperature scale, changing temperature scale. So that's why we use the Kelvin temperature scale in the combined gas laws. PV over T is equal to PV over T, initial, final conditions. All right, so this can be broken up into 3 different ways. The first one is called Boyles Law. It's not necessary for you to know these really, but it's for the Regents exam. But it is good practice to know what the different laws are. So Boyles Law has to do with the pressure and volume relationship when the temperature is held constant. And the way I like to think of this is thinking of the word boils. Boiling water is at 100 degrees Celsius. Is the temperature of water changing at a boiling water? No, it's not. So the temperature is constant. And when the temperature is constant, Boyle's law says the pressure and volume are inversely proportional. Well, how do you remember that? Well, think of the word boils. Boils, the Y is pointing down, the L is pointing up. Okay. Here's your combined gas law also. And here's another gimmick. Use the longhorn hand signal and then just twist it. As you twist your wrist, one variable goes up, the other one goes down. You're saying, well, wait a minute, there's 3 variables here. Yes. Well, yes, but remember, temperature is held constant. So when temperature is held constant, we can take temperature, this variable, we can take that right out of there. So now we have pressure and volume right next to each other. Pressure think of it as going up, whereas volume is going down. So the pressure and volume are inversely proportional. As one goes up, the other one goes down. That's the inverse proportional relationship. The word Boyles has the Y pointing down, the L pointing up. Inversely proportional. The next relationship between the gases is Charles' law. And here's Prince Charles right here. Charles is not named after him, but Prince Charles, if you think of this, the way I like to think of this is Prince Charles is under constant media pressure. So in this scenario, pressure is being held constant. So the volume and temperature are directly proportional when temperature is kept constant. All right, so again, how does that work? Well, let's look again at our combined gas law. Our combined gas law has all three variables here, pressure, volume, and temperature. And what is being held constant? Well, pressure is being held constant. So pressure, we're going to get rid of pressure. We're going to delete pressure. And so now we have volume over temperature is equal to volume over temperature. So now we have one variable goes up, the other variable goes up. And the way to do this, again, is they're right on top of each other. Okay, these two are right on top of each other. So take your longhorn and turn it up and down. So if one variable goes up, the other one's going up proportionally. Notice in my hand, as one goes up, the other goes up. One finger goes up, the other finger goes up. Charles' law, they are directly proportional. As one goes up, the other goes up. As one goes down, the other goes down. The last relationship is called the pressure and temperature relationship, also called Gay-Lussac's relationship. This is where we have constant volume. This is just the other last choice of this. This is where the pressure and temperature are directly proportional when volume is held constant. So again, we take out volume out of this equation. So take out volume, delete that. All right. And so now we have pressure directly over temperature. So if one thing is directly over the other, as one goes up, the other one goes up. Pressure and temperature are directly proportional. As one goes down, the other goes down directly. They are directly proportional. So again, all comes back to your combined gas law. The combined gas law says the pressure times the volume over the temperature is equal to the pressure times the volume over the temperature. If you have a variable that's being held constant, you just take it out of the formula and you're all set to go. All right, let's give this a shot in some practice.